Thanks to all the organizers, both for the invitation to speak here and to bringing us all together in this very nice place. Thank you all for coming back from lunch. I know that was maybe the hardest thing to do so far this morning. So yeah, I'm going to give you hopefully a gentle introduction to a line of work my group has been actually pretty excited about for the last couple of years. And it's this goal that if you come to me with a complicated driven-dissipative system, are there cases where we can actually make exact statements? And the kind of systems that we're interested in actually overlap with some of the things we heard about this morning in Anna's talk. These are often systems of many interacting qubits, many interacting bosonic modes, photons, systems where there's no obvious small parameter, and yet we can make statements that are exact. Okay, and how do we go about doing this? It turns out there's a very, very subtle notion of, of me listening to myself. Are we muted now? I feel like I'm mocking myself. You know, it's success. Okay. You could just close it, no?
I'm supposed to look at questions online.
You can do it at the end.
Okay, sure.
Okay, there we go, safe again. So as I was saying, how are we going to get these exact solutions? There's a very, very funny and subtle notion of time reversal symmetry that can show up in a lot of these dissipative models. We call it hidden time reversal symmetry because it's not obvious. If this symmetry exists, it gives us a really, really direct way of making these exact statements. It's kind of a quantum version of detailed balance. So as Jameer pointed out to me, this is a 25-minute talk. I'm going to give you a kind of impressionistic sense of what this idea of hidden time reversal symmetry is, tell you a little bit about some of the models where this shows up, and hopefully tell you about some of the physics that we've learned by using these techniques. It's not just a question of, great, I solved this, here's some special functions, let's move on. These solutions actually let you uncover physics that would be hard to see in other means. And just let me give credit to the people who really did the work. So again, this has been going on in my group for a couple of years. It's David Roberts. His PhD work really sort of set the stage for all of this work. Andrew Ligenfelter, who's still a PhD student in my group, has been doing a lot of nice stuff in this area. And then Jeffrey and Ron, I think the thing I'll end my talk on, using these methods to say something about a driven-dissipative spin chain system, they've been leading that work. Okay, so in terms of the broad context, I'm a theorist, right? How do I look at a complicated driven-dissipative system? I basically think of this cartoon here. I have a system. It has a Hamiltonian. That could already be complicated. That could be many particles interacting strongly. The system is driven in some way, right? Maybe I'm injecting energy into the system in some way. That driving is balanced by some dissipation. Okay? And so the question is, what comes out generically from that mix of ingredients? This kind of interplay, of course, is relevant to maybe any kind of experiment in quantum information processing. As we heard about this morning, it's also a really interesting mix if you're interested in new kinds of many-body physics. So here's just two recent experiments where this kind of interplay of ingredients can give you interesting many-body effects. So Anna already mentioned this experiment from Antoine Bauet's group, where there's a collection of rubidium atoms. They're driven by a laser. There's some collective decay phenomena. The interplay between that may or may not give you an interesting dissipative phase transition. Here's a very different experiment, again, in the realm of quantum simulation. This is from the Google superconducting qubits group. This is a 1D array of transmon qubits that's really meant to mimic the physics of a driven dissipative spin chain. So in this system, in the simulation experiment, they can look at how does transport work in this driven interacting spin system. Okay, so lots and lots of different experiments where these kind of ingredients kind of show up. What would we like to understand? And throughout this talk, right, I'm going to focus on a driven dissipative system that is described by a Lindblad-style master equation, right? Nothing going beyond that. But this equation could be very complicated, right? And the question I'm going to focus on is, can I say things about the dissipative steady state? So this equation will encode the driving. It'll encode some dissipation. The system will relax into some interesting, typically non-thermal steady state. Can I describe that exactly without making approximations like mean field theory, semi-classics, et cetera? Right? So why do we think that even might be possible? Without dissipation and driving, we know about the beta ansatz. We know that there are these remarkable systems where you can have strong interactions and still say things exactly. Could there be something like that in a dissipative context? So what I will tell you is not the dissipative version of beta ansatz techniques, but it's something spiritually related. Okay? So here is a smorgasbord of models that, hopefully even just looking at the PowerPoint cartoons, do not obviously look trivial. Right? So what do we have here? On the left, I have a collection of bosonic modes, cavities. I have arbitrary pairing terms. So we could call these two-mode squeezing terms or parametric down-conversion terms. So we're adding photons in pairs in this collection of modes. I also have some kind of nonlinearities, some interactions, Kerr nonlinearities. This kind of system is relevant to certain experiments in superconducting circuits. It's related to what people call coherent Ising machine physics. So here's and again, this model, the driving is the pairing. The dissipation, which hasn't been drawn here, you can imagine there's just simple loss on each of those modes. Okay, so that's a complicated looking driven dissipative system. Here's a system that looks very different in the middle, if I can get this to show up. This is a kind of driven dissipative transverse field Ising model. So this is a collection of qubits or spins. I have ZZ interactions between all of the spins. I have some Rabi driving. That's these X fields here. I have some detunings. And maybe I have single spin decay. And on top of that, maybe I even have the kind of collective superradiant decay that Anna described. So again, what happens in this system? What's the steady state? And here's a third system that, again, looks very, very different. This is now closer to that Google experiment. So this is a 1D chain of qubits where maybe I have some driving on the boundary. I have some dissipation on the boundary. Maybe there's interactions, right, in these qubits. Again, I could ask this basic question. All of these models have driving. They have dissipation. There's a many-body aspect. What can I say about them? And the kind of cool thing is there is a way for all of these models to actually make exact statements about the dissipative steady state. And the method for doing that is actually common, despite the fact that this is a bosonic model, this is sort of a more all-to-all spin model, this is a spin chain. There's a common technique that gives insights into all of these things. Okay, so what I'm going to try to do in an impressionistic way is give you a flavor of what is it that leads to these solutions, and then just tell you a little bit about the physics that comes out of the solutions. Okay, and because we're supposed to be talking about spins, I'm really going to focus on panels 2 and panel 3 over here. Okay, so how am I going to get some exact insights into this? I'm going to give you a lightning fast little introduction in how to think about time reversal symmetry in a meaningful way for one of these Lindblad master equations. Okay, so let's make everything classical to begin with. Classically, this is a classical master equation. So I can imagine I have different microstates or a classical particle that could live on these different sites. I have probabilities of the particle being on one of those sites. I have transition rates that tells me how those probabilities change. How do you think about detailed balance or time reversal symmetry in this setting? You would say, well, look, if I have a steady state of this classical master equation where for every pair of states, there's no probability flux between those states. So the probability flux from I to j is balanced by the reverse probability flux. That would be a standard textbook definition of classical detailed balance, a reflection of the fact that the microscopic dynamics had some notion of time reversal symmetry. So how do I extend that to something that might apply to a quantum system? And again, there's many, many different ways of doing this. I'm going to tell you a particular way that seems crazy when you first see it, but turns out to be useful. So let me take these classical equations. And the other thing that I should mention Classically, if you have detailed balance, it makes it very, very easy to solve for the steady state. So this constraint that there is no flux between any pair of states, that's like a local constraint on the steady state. You can use that up to build up the steady state probabilities in a very easy way. So to generalize this, I'm going to write this equation in a slightly different way, right? So I could basically turn all of these rates into a matrix. I'm going to take the square root of the rates into a matrix. I could also take these probabilities, take their square root, make them into a diagonal matrix. And so this condition here, no probability flux between pairs of states, becomes this funny condition that relates the rate matrix, its transpose, and the probabilities. Okay, so that's just a weird way of writing this hopefully more familiar looking constraint. Yeah?
Would it be fair to say that you're taking detailed balance as sort of an ansatz and then using that to solve?
Absolutely, and that's going to work the same way in the quantum case. We hope there's detailed balance. We try to find a solution that has detailed balance. If we find it, we're done. We're golden. Yeah.
Well, unless, could you potentially miss other steady states that do?
It's possible. In a lot of the cases we're looking at, because we have single particle loss, we're guaranteed to pretty much have a unique steady state. You can even ask me later on. There's even some cases where we can have multiple steady states and still use this machinery.
What about like limit cycles and things like that?
Not in the case where you have like single particle loss everywhere, even with interactions and a finite dimensional Hilbert space. There's someone's theorem whose name I'm forgetting. Yeah, yeah. Yeah, Suzanne?
Very stupid question. Why do you need the experiment?
Because you're gonna see it on the next slide. This is just a weird way of writing this thing here. It's gonna let me make an ansatz for something I can now generalize to the quantum case. So what is the quantum case? The quantum case is this generic Lindblad master equation. I could have a bunch of different Lindblad dissipators here. And now how do I generalize this condition? So the thing I'm going to do is I'm going to say, well, the square root of a rate, the square root of the rate is sort of like one of these jump operators. Okay, so now here is my ansatz, right? I am going to look for, so here I was looking classically, I was looking for some probabilities. In the quantum case, I'm going to look for some operator that relates each jump operator to its dagger in a way that's analogous to this equation here. Okay, so I'm going to look for some crazy operator psi. Z psi is psi z dagger for every dissipative term in this equation. And again, we can't leave out the Hamiltonian, right? There's a Hamiltonian here as well. So from this Hamiltonian, I could combine it with the jump operators, get a non-Hermitian Hamiltonian that was also on one of Anna's slides this morning. I'm going to insist on the same condition relating H effective and H effective dagger. Okay? And again, this is all meant to be impressionistic, right? You're going to have to trust me a little bit. This operator psi, it's also going to have to be antilinear. Okay, so it's not a linear operator. So imagine I can find such an operator, right? So what? Well, if you find such an operator, you have a steady state, often the steady state. So this operator basically squared is guaranteed to give you the steady state, a steady state of this Lindblad master equation, if these local constraints are satisfied. Okay, so just many, many more things I could say about this notion of hidden time reversal symmetry. This is one way of starting with a classical description, getting something that's quantum. Okay, it basically tells you there's a set of local constraints you can look to sort of solve that will then let you find the dissipative steady state of interest. Okay, yeah.
That way you express it reminds me a lot of how a strong symmetry, if that would be a standard operator. So do you have anything useful if you instead require your antilinear operator to obey the equivalent of a weak symmetry condition? So that action.
So this is we think of this as distinct from the notion of strong and weak symmetries, and one of the things that then yields is that this really tells us things about the steady state. It doesn't enforce like a block diagonal structure on the entire Lindbladian. Yeah.
What I'm asking is like if you were to weaken this requirement and to impose it at the level of the superoperator, like the action
I see what you're saying. I don't think I've
Does it give
thought
anything?
through what that gives. Yeah, yeah.
Definitely weaker.
I think not in terms of giving me a direct route to the steady state. Does it still tell you something? That's a good question. Yeah. I have a slightly more user-friendly way of phrasing the same condition, right? And there's all sorts of neat things about this. This anti-linear operator, you can extract an anti-unitary operator, and we can call that T. So this lets me identify a notion of time reversal symmetry starting with some abstract Lindblad master equation. Let me give the more physical, maybe a more physical way of thinking about this that will make the few experimentalists perhaps a little bit happier. So again, my goal is I'm trying to find the steady state of this master equation. Why am I writing down these weird psis and stuff? So here's like a fun way to try to solve for the steady state of a master equation. So here's my driven dissipative system. I'm just drawing it as some cavity with some loss, but this is completely general. So when excitations leave, let's just think of it as loss, right? You know, they're gone forever. They go into the bath. I can model the dissipation in any way I want. So let me model the dissipation as a chiral waveguide. So these excitations go into this channel. They fly off to infinity. They never come back. And then what can I try to do? Well, let me try to put something downstream this chiral channel that basically absorbs everything that has been emitted by the original system. So this is the real system, the thing that I care about. This is some auxiliary system that I'm putting into the problem just as a theorist to let me get a solution. And the idea is if I could find a system that absorbs everything, well, then I can solve for the steady state of this. This composite system will then relax into a pure state of this doubled system. If I take this pure state, trace out the fictitious thing, I have the steady state that I'm interested in. Okay? So in general, this is as difficult a problem as the original problem. If you have this notion of hidden time reversal symmetry, you know what to put downstream here. You basically put a copy of the original system, but the Hamiltonian goes to minus Hamiltonian. Okay, so that turns out to be equivalent to that crazy thing I had on the previous slide with these psi operators. This is another way of phrasing this constraint. The upshot of all of this is there's a funny notion of time reversal symmetry that kind of gives you an ansatz you can use to really look for steady states of these complicated Lindblad master equations. And this technique works for a lot of interesting systems of interest. Yeah, Jimmy.
So I technically understand what's going on. Also the cartoon, very nice. But I am conceptually disturbed. So no.
That is always my goal, so I'm
No,
glad to hear that. Yeah.
No, but I can tell. So it cannot be fully time reversal because dissipative dynamics is not reversible. So what?
Yeah, and this is why this is, yeah.
You're calling it time reversal because you're technically employing the same trick.
So I'm calling it time reversal because there's an anti-unitary operator that is relevant to the system. If we want to really think about, like even just classically, right? If I have classical dissipative dynamics, I don't have reversibility. So what you could ask for is something like Onsager symmetry of correlation functions. And I will save that for the coffee break. There is a direct way in which this T and this symmetry I'm talking about gives you a particular kind of Onsager symmetry. But yeah, it's a very subtle way in which you need to think about what are the consequences of having a T that is relevant to the system.
But then there's nothing time reversal here.
No, there's a notion of, there's a class of correlation functions that are the same at positive and negative time. That's guaranteed by this symmetry. Yeah.
But to be clear, it's not a symmetry of the dynamics?
No, it's not. That's why we call it hidden time reversal symmetry. It's not like a symmetry in the sense you learn about symmetries in grad quantum 1. Absolutely. Yeah, and it's not the same, if you're familiar with the language, as a weak or strong symmetry. And am I down to 4 minutes? Or yeah. OK, we'll get to some physics in a second. Yeah.
Okay, maybe I'm not quite processing all this in real time, but could I, doubling of the system, can I not always do that, or is the question?
You can, but like the point is when you double the system, you want the doubled system to relax into a pure state. And so the question is, what should I put downstream here to ensure? Think of this as like an infinite waveguide. In general, there will be stuff going out over here. which means you doubled the system, but these two things don't end up in a pure state. So I want the real system, this fictitious thing I put downstream, to relax into a pure state. And then the question is, what exactly do I put downstream here? This symmetry tells me I don't have to do any work. You just put exactly a copy of the original system. And I do apologize. This is not meant to be something that you can digest in 3 minutes. This is a lot of work that's been condensed to 3 slides. But this is, again, giving you like a flavor of what the ideas here are. Sure.
Maybe I missed something. What do I know I can find a site or what sort of?
You can't, right? It's the same thing with classical detailed balance, right? So you just try, and if this works, you've got a solution. It's great. If it doesn't, you can't use this to solve your system, right? So it's, and to be completely honest, if you come to me with a system, I can't look at it and go, oh yeah, you have this symmetry. I will try, and if I can solve it, great, I can tell you something. If I can't, I can't. And that's often the way you have to use detailed balance, even in fully classical situations. Yeah?
So there, for example, you write chiral waveguide.
Yeah.
And then you would think that, is it really about time reversal symmetry or non-reciprocity of this waveguide? Because trying to play with similar concepts and a solid state path is not just about the time reversal symmetry, it's also the inversion. Like you want something that is non-reciprocal.
Right. So this is, again, this is one way of thinking about the construction. This is a way that's equivalent to thinking about the construction, where there's no doubled system, there's no chiral waveguide. Why am I talking about time reversal symmetry? This operator psi has to be anti-linear. It's anti-unitary part. That actually has some meaning as a time reversal operator. OK, so maybe in the, what do I have now, Derek? Like minus 2 minutes or something?
With this question, I mean,
OK.
it's 7 minutes in total, including.
Yeah, and you had the iPad problem, right? So I get a minute for that. Let me, and I'm here for the whole workshop. I'm happy to attempt to demystify some of this. Let me just tell you about some of the physics that comes out of using these ideas. OK, so let's just zip along. So here is one model that is in some ways related to things that Anna was talking about this morning. So this is a model of a bunch of interacting qubits. We have all-to-all ZZ interactions. We have Rabi drives on each qubit. The Rabi drive amplitudes could be different on each qubit. These omega j's don't have to be the same. We have single qubit loss, and we have collective loss. OK, so if you stare at this, and I have many qubits, this is not an obviously trivial problem. It's not a collective spin problem. It doesn't have permutation invariance, because the Rabi drives could be different. This is solvable using this technique. So this system, no matter what the parameters you pick, there is a psi. It has this quantum detailed balance. Yeah, Anna?
Yeah, so this is very fascinating. But so if I look at this master equation, you have this collective decay symmetric, right?
Yeah.
So what if it's not? And also what if I mean, these are not really icing interactions, right, in this type of graph. So can you really capture a master equation that would really involve multiple jump operators that are...
Geez, I was happy that we could solve this, but I understand you want more. You know, geez, people are never satisfied. This is an interesting question, and there's a student who's looking into this. Like, what else can we add to this model and still preserve solvability? We know, for example, we can replace the Ising interactions by XY type interactions. I will also show you in the minus 2 minutes I have left, a model that is not collective at all, that is also exactly solvable, which makes us think that there are ways to deform away from this and still have things, right?
But it feels like a bit maybe perturbative, right? Like if it's like power law, you cannot do it, but maybe if it's source symmetric or nearest neighbor, maybe in these two limits you can, and in between you hope for the best.
This symmetry is so weird. We don't know if there are other solvable points in terms of things you can add here. Yeah.
Thank you.
If this question is too detached,
OK.
each of these points would have exceptional point. Each of these systems would have its exceptional point with individual Rabi drives and individual decays. But you spoke about collective decays. Would there be some sort of a generalized phenomena for all of the system?
I don't, like, in terms of how we've understood this, I haven't, thinking about exceptional points hasn't been particularly useful, right? So this system has a unique dissipative steady state, and I'll show you some interesting features of it. This has some phase transition physics that we can get some insight into from this solution. And just to have like a pretty picture, let's even skip the form of the exact solution. Here is something the exact solution can show us. It can show us the emergence of phase transition behavior as we increase the number of spins. So in this model, I'm driving these spins. Delta is a detuning, right, of the drive from resonance. I have interactions, maybe collective loss. And so what you see is, if I have a small number of spins, that's this pink curve, I see some discrete resonances. As I go to 16, these resonances get closer and closer together. By the time I go to 128, I have what looks like a sharp first-order phase transition. Okay, so the exact solution, this is just one kind of neat insight that comes out of it. We can see the transition from few spins to sort of mesoscopic to the thermodynamic limit. We can see the emergence of a phase transition. I'll take the question in a second. The dashed curve here is what you get if you do mean field theory, right? Mean field theory is getting this branch here correct and this branch here correct. Where does the first order phase transition occur? Mean field theory does not tell you that. A standard Maxwell construction also doesn't predict the phase transition correctly, right? The exact solution tells you that. Susanna?
How does you're solving this scale?
You mean?
System size. Because system size obviously.
Oh, it scales very well because I can write analytically the solution down. So this is an analytic form for the solution with all of this. Yeah, sorry. Yeah.
So you can basically just plug your in.
Yeah, and so I think now David has gone to like thousands of spins. Yeah, so this is, yeah. And I'm looking at Derek. There's one more model I want to flash up in like 2 seconds. Yeah, and I'm out of time. Can I do that and then take your question? Is that okay? Okay, so just to, there's all sorts of other pretty stuff. Here's a very, very different model, and I will just end you with like another cool plot. This is an interacting spin chain. This is an XXZ spin chain. Here's the Hamiltonian. We're going to have loss just on one site, and we're going to have driving on the other site. The driving, again, it's going to be a coherent drive, this kind of Rabi drive. So this is an interacting, albeit integrable spin chain. What's the driven dissipative steady state? So this is something we can also solve with these techniques. Okay, and so again, one way of thinking about the solution is, here's the original system. We model the loss with this fictitious chiral waveguide. We put a copy of the system downstream. Everything relaxes into a pure state. And that pure state has an interesting infinite dimensional MPS form that one can solve for exactly. So what's the pretty picture? Here's the pretty picture. This model has some really surprising driven dissipative phase transition physics. So think of this as like the density in the steady state. What's the density of excitations in these qubits? The x-axis is the drive amplitude. The y-axis is this delta parameter, so the ZZ interaction between neighboring qubits. So what you see is there's regions of high density and low density. This low density regime where delta is large, that's no surprise at all. You're tuning a parameter of the bulk spin chain. That's something that corresponds to physics of the bulk spin chain. This transition, as I go from left to right, is a surprise. You're just tuning a parameter at the boundary of the spin chain, and you have a continuous phase transition from a low-density regime to a high-density regime. Okay, and so that's something we can understand this phase transition in a lot of detail. This phase transition and this critical driving strength doesn't correspond to some simple, obvious parameter in the bulk XXZ chain. Right? And getting this kind of phase transition just from boundary driving is kind of unique. Okay, so Derek is starting to menace. So I'm going to skip all of this, and you can bug me about it later. I realize this was a lot for a 25-minute talk, right? Hopefully it will have confused you enough to you will bug me during the coffee break. Yeah, I will stop here, and if there's time, I'll take some more questions. Thanks.